panel is over, I will do a quick recap of yesterday, things that leading to where you are. So hopefully, as you have sat down, you have looked at the papers and located on the whiteboards. These contain the names of the team members that should be at the table or adjacent table to you. Specifying also the problem that you hopefully have signed up for. There was a few that we weren't sure where to put because it just wasn't enough sign up. So, but here's the deal. We're going to take you through again a few other exercises today that will help you take this this problem statement, some general ideas of some issues facing what you identified yesterday, and formulate it into a very clear, concise problem statement that will allow you to then create a solution around. So those activities will go on throughout the morning here, and then right about lunchtime or right before lunchtime, that's the hour that you're going to have, or to give you a whole hour to really dial in a solution. Together a concept poster. We'll show you exactly the format and give you some pointers on how to present that. Because after noon, after lunch, you will be presenting. So get your singing voice ready, jazz hands. It's time to show off your concept. You will be competing for this lovely collection of engraved mugs. And so, to the winner goes the victory, and to the prizes. So we will have judges here who will be kind of assessing each pitch. We'll go around the room making a pitch, and we'll be presenting the exact criteria, so you guys know very well going into it how you will be assessed. And then we'll do some wrap up. So to get things kicked off this morning, I'm going to hand it over to Mike to say a few words and introduce the panel.
Thanks, Aaron. I did want to make one comment here. As you may or may not know, the Robotics Factory has been out of a group called Outlive Gear, which is an incubator for hardware startups. So we do we get our hands dirty a lot. So I want to thank Matt for actually creating all of those. When I say did it by hand, we still use a laser to do it, but it wasn't sent out to some third party. This is something we did in-house, so kind of cool. We want to add a little bit of personal flavor to that. Cause amongst our society thing to play. So what we want to talk about today, we had a conversation about this before, was kind of demystifying robotics automation. Elon Musk is up there, and every day we're going to be flying the moon and flying taxis and autonomous cars. We're going to make breakfast story and all this nonsense. None of it's true. There's some of it is true, but a lot of it is not. And for those of you who are not in the industry, we want to kind of debunk some of that and tell you kind of what really happens. We have these conversations all the time. My last company was a robotics company, and we had Slack channel. Every time somebody would say something stupid, we'd all talk about 100 reasons why they're lying to the world. So this is a little bit of insight into what really happened. So I want to introduce you to the panel. Spencer Krause is going to be hosting it today for us. So Spencer gets the whole runway thing. Spencer, come on over. Take whatever you want. Kevin Dowling, Kevin, the author of the Robotics Network, but you've heard about here a little bit over time. Bojarski, I don't know his actual title, but he's a big, smart nerd in Caterpillar. So we always want to work on something and want to get on a big and then Ray Russell. Ray might have put more robots in the field than any human being on the planet, and they've been all over the planet. Literally spent how many years in Australia?
3 years in Australia.
3 years in Australia. So the conversation we had before was we talked about when things go bad as a disease. This is the dirty underside of what really happens. We have literally have battle scarred fighting robots over time. There's some those battles. This is not fluff. This is not nonsense. It's real stuff. It all sounds like it's part of the job. It's all very doable and it's all very achievable. But there are bumps along the way. Yeah, they're taking on robots, metal and steel. So anyway, with that said, you guys want to thank all of them in advance. So thank you guys for coming down here. And I hope you guys enjoy.
Thanks for that lovely intro, Mike. So yeah, I know it's been early in the morning. Appreciate all you making it out. Really excited to talk to you here about some of the sorts of robotic stories you haven't heard in the news or from Elon Musk, as Mike put it. So, as Mike said, we've got 3 of the more accomplished field roboticists in the field. Excited to have Ray, excited to have Ray Russell, Lou Bojarski, and Kevin Dowling here. So we're going to get started here with Kevin. Kevin, tell us a story about a time a robot didn't go the way you expected.
Which one? Say the first generation of roadworthy autonomous vehicles that we built in the 80s here at Carnegie Mellon, there was always a challenge. But one of the things we did that actually stepped up our game quite a bit from the indoor machines and the machines that wandered the sidewalks and campus was the ability to convert a roadworthy vehicle into an autonomous vehicle. And that was a Chevy 350 van. And we actually put the researchers on board, the computing on board, everything on board. All sensing, perception, actuation was in one vehicle. So it meant that the students, if the computer crashed, the machine could literally crash. And fortunately, it never did. That vehicle didn't. But previous vehicles had tried to climb trees because they were looking at the shapes of the roads and trying to follow it. The tree looked like a road if you sort of squinted. We had incidents where we were pushing a robot, for example, which was nominally unpowered in order to set it up for staging for an experiment. And it actually powered up the system because the back driving of the motors caused the motors to generate electricity, which then triggered the power on circuit. So these are hard problems, and every problem becomes a potential solution or set of solutions through which you continue to build that. We had a lot of continuity. CMU also had a very strong staffing requirement, which many universities don't have. So the Robotics Institute, which is today 900 people or more, is also staffed with staff who are there permanently, or at least for some extent of their career. So it meant that there was a lot of knowledge built up that could be transferred to the next generation of roboticists. So for many, many years, 30, almost 40 years now, there's been an ability to draw upon that. And then those folks are here in the industry and so forth. So there's a lot of sort of funny and some not so funny stories around that, but with every one of those, we learned more. And if you told people today, before autonomous vehicles existed, you're going to make a self-driving car, even back then and still today, people are saying, oh no, it's just not possible. There's a long tail of things you have to overcome, contingencies basically. And if you can't solve those problems, you're never going to deploy them. But we are substantial, and these are hard problems.
Let's kick it over to Lou. That was great, Kevin.
Kevin, you hit on a good point that a lot of times, especially traditionally, we were taking existing hardware, automating it, adding perception, planning, positioning, that sort of thing. Even in Caterpillar, we still do that for development. We make new hardware, so we're always adding things, and that was, like I said, traditionally how we've done it. We were working on programming in other companies that was UAV. It was we weren't doing UAVs. This is 15 years ago, so drones weren't as superb as they are today. So we took it very seriously. Layers of safety, test site, secure 40 acres of open ground, man person ground. Really took it seriously. And the software engineers who were working on it, we had a really good stack. We were interfacing with the avionics stack on the machine. We felt really good about the field. Hired again, 15 years ago, hired a licensed UAV pilot, which at the time, today, Tripo, I think there's some of this weird probably. But at the time, we saw our So anyway, we were very confident about the field for this test, not in front of the customer, thankfully, based on how this goes. But one of the industry partners yesterday hit on a note where make sure the problems you're solving fit in the system or don't cause other problems. Make sure the interface to the next part of the problem, your solution marries up with it. So kind of in the spirit of that, as we were in final testing, there was some discussion as to whether to use UAV, at the time, maybe $30,000, $50,000 UAV, we're going to crash this thing. Yep. Decision was made, we're going to hold position. GPS waypoint following, just full position. Operator can come in, land the thing safely, live to fly another day. In the final ramp up to the testing though, for controls it got a little choppy. There were some small intermittent interruptions and comms. So you didn't really have a nice smooth flight path. It looked bad. It looks bad. How do we smooth that out? Let the software engineers work on it. And they came up with an idea, well, this whole objective is we're only losing comms. Small. So you take the field, everything's going good, and we never experienced a sustained loss of communication. So if you have a sustained loss of communication and you're holding trajectory not position in a UAV, it flies away. And unlike on road, that operator really can't get control of it fast enough. So kind of the crash and burn story is thankfully not in front of the customer. Thankfully, great layers of safety, so there was no impact or danger to the person or any of the testing staff. We crashed a $50,000 UAV. The response we do enough to give us 2. So we had a backup.
Nice.
It eventually worked. But yeah, that was kind of probably the biggest crash and burn that I've seen that was a good learning experience.
I think guys augmented your control strategy after that. I wasn't involved as deeply. The lesson learned was that it was not binary, right? It wasn't an either or. It was a much more sophisticated strategy for how we dealt with. It was conditions, right? It was condition-based systems engineering. What get into a little bit of the geeky, the failure modes, what the FME look like, and how does that impact the system? Makes a lot of sense.
Yeah.
That was great, right?
I'm just gonna stand up. I think everybody will be able to hear me. I have a difficult story, so I have to stand up to do this. So this story is about 20 years old, and like my father, my stories only get better as time goes by, right? But the bare bones of the story have not changed. And the customer and the people involved will not be revealed, so to maintain their innocence. But anyway, it was we were tasked with building a 2-wheeled robot, self-balancing off-road. So basically, if you can imagine, a Segway with like a 55-gallon drum on top of it. That basically is what it looked like. And it ended up having like $50,000 worth of sensors, because in the old days, we didn't call them LiDAR, then they were lasers. They were $15,000 a pop. So it was gonna have all this expensive equipment on it. So somebody thought, hey, before we put all this equipment on it, we ought to put like training wheels on it. And then, because we're gonna have to add some self-balancing to it, and the thing falls over, we don't destroy $50,000 worth of equipment, it just ends up on the training wheels. So I got tasked with building a training wheel system, and we set a date for when we were going to do this. It ended up in the back of a 1-stall garage that was 3 stalls deep. So you can imagine a very narrow stall, and we were at the very end of it. Garage door on the far end, which on that day was open. Looking back now, I don't know if that was a good thing or a bad thing, but the garage door was open. So anyway, we set the robot up. The software guys turned on the self-balancing routine, and the robot's kind of sitting there doing this. The original manufacturer of this device gave us access to all the software. So we inserted our little subroutine to do the self-balancing, but all the rest of the software was the OEM software that came with the robot, which we did not look at close enough. So the whole thing was, the software engineer was just going to hit a button and kill the self-balancing routine, and it was just going to flop down on its wheels, and that was the test. I had a little e-stop button on it, so it caught on fire, turned power off. So what we didn't know was inside that OEM code, there was a statement that said, if the angle of the robot exceeds more than 35 degrees from vertical, the motors go to full power. And the idea was, if you've seen a Segway and somebody loses balance on it, like Ford, they put motors in the opposite direction to get you upright again. Okay, we did not know that line of code was in there. So the software engineer reached over and hit the button that said kill the self-balancing routine. The robot went thunk. Motors went to full power, and it was gone. And I don't mean like gone, like trundling down the hall. I mean gone down through the garage, out the door, down the driveway, across the street, down over the grassy banks, 4 lanes of traffic, grassy bank on the far side, through a grocery store parking lot full of women with strollers and guys pushing grocery carts and kids walking little dogs. And it ended up against a brick wall and a furniture store at the top end of the parking lot. This happened in about 15 seconds. And mostly it was
5 engineers sitting there with their mouths open thinking, boy, we did not see that coming. There's the end of our career. We're about to spend 3 years with personal injury lawyers. But luckily nobody got hit. You couldn't thread that needle any straighter than it happened that day, but nobody was hurt. And I remember thinking when I was sitting there watching that, e-stops are no good if the robot can go faster than you can run. So that was the epiphany I had that day. And I can't ever look at an e-stop anymore today without that image coming in my mind. So the moral of the story is wireless e-stops are a really good thing. So, but it ended to go. And I think the moral of the story is there's not much difference between deep experience and a bad outcome other than your dumb luck. So, and that day it was sheer dumb luck that we didn't hurt anybody, but it was a lesson I learned.
That makes a lot of sense. That's awesome.
Yeah, thank you.
So, what are some of the things that you guys have learned from some of those experiences that have sort of helped you keep from doing it again? I know. Say in robotics engineering or business, I journal it, and then I go back and I say, if I follow all these bullet points, I won't make the same mistakes again. What are some of the lessons? I mean, you guys have been pioneering the field, for longer than I've been alive. So,
Thanks.
but yeah, it's just for the audience.
I think a big part of it is recording it and analyzing it, and then finding a solution to it. So as we went through multiple generations of robots that we were building in the labs, we would take those lessons learned. So one example is multiple generations of robots. So by the late 80s, early 90s, we were building a 6-legged walking machine that stood 4 meters high for Martian. It was a NASA-sponsored project for the Martian terrain, and it had a very unique configuration, almost like a giant egg beater, where the legs could actually circulate through the body as it was walking. It was a static walk, so it wasn't like a Boston Dynamics machine you might see today. But one of the first things that we architected into the entire system was a safety circuit. That safety circuit had a watchdog, a heartbeat, and if that heartbeat failed, so it would actually address some of the issues that RJ mentioned. It lost communication within milliseconds, find out. What was that?
So that's awesome.
Yeah, it was just, but that was a lot of effort in itself. Sort of, some of the researchers who wanted to do more of the perception and vision using that machine, it's like, well, why are we to do all this? We don't do this. So we had a couple hundred hours of work just in designing, constructing, and testing the safety circuit, isolated from everything else, long before the whole system got up and had the capability of doing that entire cycle of perception and maturation.
That makes a lot of sense to me. And the only way you know to do that is if you've seen something explode at some point.
Yeah, we never had that, of course.
Is this loud? Proximity is the issue.
Yeah. I think for us, post-mortem after your first field, or not field test your lab, that's stand it up and get it in the field and take your back guard field. Hopefully, we can parking lot or street. Don't take the confidence you get there once. You talk about it's like, hey, it worked once. It's like, well, it's got to work. Not only 4 months, but that's the work. There's time to pass it. That's the work. And a big lesson learned you've taken is some of you mentioned it yesterday, it doesn't count those on the machine. No particle credit. So you're in the field. So get that field follow, get on that machine, get all that. Get those known, get those unknown, make those unknown known. Right? Something is there's so much that happens when you put it on the machine. Do as much of that diagnostic approach. Force yourself to fail fast. Try and leave. That doesn't succeed. In the hard part, this is important, is getting access to those machines, getting on those machines, building surrogates, all those sorts of things. They are expensive. Program managers don't like it. Sometimes sponsors do. But the extra cost of getting them paid on the space.
Yeah, we're talking about
or the engineering groups.
yeah.
That's $10,000 is a machine. Cheap.
Yeah.
Please bend it and we'll test everything.
Yes, for me, you know, that like the more specific things are like just make sure we have control of power, right? You always want to make sure your communication is your power system. You got to be careful there because sometimes killing the car can lead to other things down the road that you think it just doesn't stop. Like if it has brakes and they don't come on when you kill power. Another epiphany. And one of the things is I'm over the years I've become very vigilant about the robots are testing, especially when you've done lots of miles and they start getting mature. That's usually when you really get bit. We lost palms on our ag robot in Australia. Luckily, it was out in the middle of a giant 8,000 skill, but had been running fine for months and months and months. Just a momentary blip in the GPS where suddenly it thinks it's 300 feet from where it had been, and luckily it's not hit. But still, it was a good example. We hadn't wirelessly stopped kill it immediately, but you never can turn your back. They're like bad dogs.
Yeah, absolutely. So I guess I'll get one story in too, since you guys hold it. You guys know. Yeah. So when I was a student at Carnegie Mellon, there was about a 150-pound robot that was sitting in the box club, and they don't teach you about certain things at university. And one of the things they never teach you about the same curriculum, unless they've changed it since I was there, is emergency stops. So you don't really, it's that weird red and yellow button that old people put on the bus. And so it's like, we don't do that. What's that for? And so we have this 150-pound robot with no emergency stop, and there's a thing called PID control in robotics. You don't really need to know this, but what you need to know from this story is that there's 3 sliders that you adjust to make the motor go where you want it to go, and one of them is called the eye slider. And when you slide the eye slider too high, the robot motor will go further than you wanted it to go. So anyway, I got a 150-pound robot with no stop, and I slider was way too high. And I'm trying to drive around the side, and I'm trying to go stop short of the wall. So it's a fun story. So in conclusion here, it's inevitable when you're pushing the boundaries of technology, and you're going to break some stuff. Things don't always go as planned. We blew along and something. What happens today? So it sucks. But in Pittsburgh, we've got really advanced technology because we've learned these lessons the hard way, built on a good base of experience. I can leave you with nothing else that you should invest in Pittsburgh because we've done hard work, built the best robotics expertise in the world. Thank you. Any questions? All right, I think we'll just open it up. Thanks.
Thank you.
Okay, good. So we're just on to day 2. Looks like most everybody has. So what we're going to do is, and because the sign up, we'll have a great flight and stuff. Okay. Now, forward. Everybody know what that table is on. Does anybody feel compelled to move around? Does anybody need more of robotics? Robotics heavy? Seems fairly
so typically these people over here, you mentioned aviation for robotics. So the other people are maybe on robotics. We didn't
Chris?
We can leave you guys out and like instead. Anybody needs it. This is for a second, guys. Both of them trying to get folks. Does anybody take supervision? Anybody use it? Okay, you got $7 on your table. Bring them on. Okay, all right. So let's just make sure we have at least a lot of mitigation at every table. Anybody who does not have at least 2 and 2. Our professional please. Okay, here we go. Okay, it's not I'm going from here. You want to use it for it? That's okay. Those bullets. These are these people are like split the baby or get what we do. What is the focus? We need one more radiation burst in the alignment on human the sun. For property. You might want to know that like one radiation. Like came over here to this drain. So let's get kicked off. So yesterday there was a set of exercises we were in through. We started the morning off learning about category, generated ideas, state of the union, if you will, with regards to these categories and finance of broken corn.
organize these in clusters, these clusters, problem statements, these problem statements. We're going over and you are now collectively sitting in the output. Again, what we're going to do, the final topic today is this, concept. This is your opportunity to solve the problem that in a semi-creative way. You don't have to document this right when it comes to time to do this. I'll put this back up. But this is generally the format we're following. Have a title, value proposition, who it's for, it should identify its title, and what measure success. So we're calling it out and make this somewhat able to see. Every team will have 5% per day. Two less teams, able to maybe able to spread that out a little bit more. Yeah. So again, to get us all in the right space, so you know what we're targeting, we're going to take this the other day and reform it on the consequences of a state of startup. We're going to give you 3 points that you can start with. The general structure of these statements are look something like this. The first prompt will be how might we or fill in the blank to the user. So fill in the blank is great blank is intended. So let me give you an example of you might take that problem statement that's on the board and turn it into this statement. For example, yesterday I had one of my problems with the lack of that Intel causes. But I would take that statement as how might be a access failure for travel. So I'm concerned about. So this statement of who the intended user is, or what specifically I'm trying to solve, trying to identify the consequences. Now, how do you formulate these is important because it will actually affect who you're targeting on the solution. So we give you an example. I'll do another statement starter. In this way, what ways might be? I'll still stick with making the access available for travel. So that this time, say the airport has been very important. However, change the user of the intended or the intended action. By doing that, you formulate a whole new solution or a solution around what that problem is. I'll leave you with one more. And so in this context, we will do a GUI rotate take back. For example, everyone always knows in similar same problem, kernel, a different state, and it completely changes the nature of the solution. This is now no longer about the OIM itself as a fact. These subtle variations will produce different ones. So, what I'm going to do is over the next 5 minutes, your goal is to create problem statement that encapsulates the problem that you've identified. You can do this in different ways. Select the problem cell. You can take the yellow stickies and write individually series of problem statements and vote them. This one I'm going to leave to the team since again, today is a lot about collaboration with the Krause. So I'm going to leave it to you to determine how you are writing. So at the end of this, what we need to know is what generated problem statement for the problem. Again, 10 minutes, the staff, the coordinator, as they generated these stickies, that they do it that way, put it on the board, or if they're collectively doing it, help them facilitate to say. I'll give you, since 5 minutes, 10, but we'll start there. You're good about we don't this is talking about
Yeah.
These things that everybody does.